I think all of you have ever heard of the word impulse, impulse, impulse. But do you know what actually an impulse is? So it is simple. An impulse, or you can call it an action potential, is a rapid and temporary change in the membrane potential. In the membrane potential. It's rapid and temporary change in the membrane potential. And we are going to see what membrane potential is. Okay? We are going to dissect word by word. We see how does it occur and what is an impulse, what is that membrane potential, okay? To bring about transmission of message from the point of reception up to the brain for interpretation and then sent back to the effectors. So now most important type of electrical signal in our cell and coordination at large. It is the most important because imagine, I usually use this, you touch a hot object, but that speed at which you're going to withdraw your arm, that speed at which you're going to withdraw your arm so that you can run away from danger, okay? Yes, it has something to do with these electrical impulses. So how it is generated, and then how it is transmitted up to when it reaches the brain. It must be some good science that nobody should miss. So when a neuron is stimulated, of course, the neurons mount an action potential, okay, which is an impulse that allow them to communicate with other neurons, muscles, and glands, so that you see a change depending on what you need. If it is just transmitting from one neuron to another neuron to another neuron, then this neuron will be able to communicate together due to this change in membrane potential, or you can call it wave of depolarization. Let me introduce a new word. So due to this wave of depolarization, if it is from a neuron and the information is to a muscle, it is still the same thing due to this wave of depolarization. Okay? To a gland, because these we have seen that some impulses might be sent to glands to impact, okay, to stimulate a gland to release a hormone, and we saw one of them is adrenomedulla, and in production of adrenaline, okay, there is an impulse involved. So depending on the course of action, then it will determine, okay, and so there are these action potentials, the so-called impulses that bring about changes in behavior. So you can have a look at this. This is a neuron and this is a cell body. So the impulse has been transmitted, okay? It is transmitted along this neuron, okay? And somewhere here you have another neuron, you have dendrites, and these dendrites will make synaptic connections with the dendrites of another neuron. And so the transmission becomes that continuous. Is that okay? Yes. So in case you have a question, feel free to drop it in the chat box. I'll be glad to attend to your question. So that is literally what an action potential or what an impulse is. It is that wave of depolarization. It is a rapid but temporary change in membrane potential, which usually we refer to as a wave of depolarization. And it is that wave that is able to transmit signals from the receptor or from the point of reception to the point of interpretation to the point of effection. Okay? Now, you should be wondering, what is that membrane potential? What is that wave of depolarization? But what is that membrane potential? Now, but before we talk about the membrane potential, this action potential or this impulse of yours, it occurs through waves. Okay? Through waves, or you can say different stages. And these different stages just occur within milliseconds. Hmm? I don't want to say in a blink of an eye, because even a blink of an eye is too big for them. Imagine you touch a hot object or you get pricked by a needle or a nail, by that speed at which you are going to withdraw from. Let me first attend to this one. So we were still on the action potentials, and we were saying that it occurs in phases. And the first phase, it is depolarization. Okay? And depolarization comes from you depolarize. Now, a membrane, it is polar. What does it mean? It has charges. And usually when a membrane is not conducting, okay, any impulse, it is usually positive outside. Okay? Positive outside and negative inside. Now this is a membrane in a resting state. And we call this one a membrane potential, or the resting membrane potential. And if you remember well, in diffusion and facilitated diffusion, this membrane potential is important as far as diffusion of molecules is concerned. So now we call this one polarized. This is polarization. Okay, the membrane here is polarized. Now, depolarization means distorting this. You are trying to restore, okay? You are trying to restore back the membrane potential to zero, okay? You are depolarizing, okay? Yes. And in the end, when the membrane becomes polarized, then the inside becomes positive and the outside becomes negative. And we are going to see how this is maintained. And so when you do that, then we call that depolarization. And the action potential has this phase. Okay? For you to conduct an impulse, you must pass through that depolarization phase. Now, we are trying to explain what depolarization is. And a neuron in its resting state, a membrane is said to be polarized, which is this, having charges. Okay? In both between the outside and the inside. Now, the charges on the two sides are different, like how you're seeing, where the outside is positive and the inside is negative. Now, that is a membrane that is not conducting any impulse. That is a membrane in its resting state. Now, depolarization means that membrane becomes despolarized. Okay? And now, this one is inevitable. Some calls are inevitable. Wanji mzee? Taka nteriro. Otesimu yanga kora chi? Ohawe na arani? Arinkai? Eh. Ha na ndiyo mukirasi haze shahe jinza mutera shana kunda amari. Ntaro shonge. Yeah, it's okay guys. Some calls are inevitable. But we have to cut them short, like how I've done. I've tried to cut it short. So now, that is depolarization. So this membrane in its resting stage, okay, it is said to be polarized, like how you see. So depolarization means to make the membrane less polarized, okay? Yes. And therefore, the membrane potential becomes less polarized as it moves from a highly negative towards zero. Then briefly positive. That is if you overshoot. So that is what depolarization means. And we are going to use these words. We are going to use these words. Okay? Yes. So in case where you get berserk, you can feel free to contact. Now, how about repolarization? Now, it is just re. Yeah, usually make life easy. Re and D. Now, re meaning means you repolarize, you gain back. Okay? The membrane potential. This is the polarization of the membrane. So it is as simple. So membrane potential back to negative. Is that okay? So you bring back, remember, the outside, the membrane, when it is not conducting, the inside is always negative and the outside is positive. So repolarization means regaining back. Depolarization, you are bringing this outside negative, you are bringing it back to zero. And inside negative, and you are bringing it back to zero. But it might slightly go beyond zero, as we are going to see, and it becomes positive. Okay? But you are depolarizing. Then repolarizing is bringing back, okay, the membrane potential. Now, there is a hyperpolarization phase. Now, hyper means too much, okay? Too much. Then polarization, yeah, kinda. Polarization means having a negative charge. Now, with hyperpolarization, you are polarizing the membrane, but you overdo it beyond repair. Okay, it can be repaired, but you overdo it, okay, beyond normal. And so you want to, let's say you want to create 10 negative charges inside the membrane, but instead of creating 10, you create 12, okay. Now this one, it is hyperpolarization, and it cannot stay in this phase, but rather it will be brought back to the 10, to the normal level. Then, so membrane slightly more negative than the resting potential. So what do? You bring it back. So basically, this is what we are talking about. Initially, you have your membrane that is not conducting any impulse. So this will be the resting potential. And we are saying that the resting potential, the inside is negative. Okay? So you can see it is negative 70, okay, millivoltage. So you have, if I'm to use simplify, if I'm use some simple language, you have 70 negatives inside, okay. Now that is a membrane that is not conducting anything, and this one we call it the membrane potential. The membrane potential, you are going to find it on the next slide. Then the membrane that is conducting an impulse, it is going to be depolarized. This negative is kind of taken to zero, okay, but you overdo it that you even end up shooting to positives, and you have positive 40. So we call this one depolarization. But after the impulse has been transmitted, then you have to restore back the membrane potential, okay. And so that phase, we call it the repolarization phase. Now you see, you restore but you end up overshooting. This is supposed to be the normal, okay, but you overdo it. Now this over we call it the hyperpolarization. You have overpolarized. So as a result, you have to restore back the membrane potential. Okay? And so it goes back to the resting state. So basically, that's how it is. And this is what an impulse is all about. Okay? Yes. So I'm attending to any question. Now, the membrane potential is that potential difference or the net charge between the outside and the inside of a membrane that is not conducting, okay, any impulse. So that potential difference, that net charge, okay, of a membrane that is not conducting any impulse, okay, we call it a membrane potential. So if this is your membrane, okay, sorry for this one. So if this is your membrane, the inside of this membrane is going to be negative. Why? You have more of the negative ions inside. And what are these negative ions? You have there the chloride ions, you have there the nucleic acids, which are highly charged. You have there the protein molecules with high negative charges. So the inside is going to be negatively charged, and the outside is going to be positively charged. Why? Because you have there positive ions. And which positive ions in this case? You have the sodium ions. You have many of these ones, a lot of potassium ions, sorry, sodium ions. And so because of these positive ions outside, very many of them, to balance the positives between the outside and the inside, then you have more, you have some potassium ions inside. Okay, what are these potassium ions for? To balance the positive charges so that they don't go beyond what the membrane can hold. Okay, yes, so this potential difference between the outside and the inside is what we refer to as a membrane potential. So the inside of a cell is negative relative to the outside. Why? Because of the unequal distribution of ions. And which ions? The potassium ions and, sorry, the sodium ions and the potassium ions, where you have more sodium ions on the outside and more potassium ions inside, but the concentration of sodium ions is relatively high compared to the concentration of potassium ions. In other words, the number of positive ions out is high than the number of positive ions inside. So the inside ends up becoming positive. So the inside ends up becoming negative and the outside becomes positive. So basically that is it. So source of potential energy, because of this difference in the charges, the positive and negative charge, it becomes a source of potential energy, and this charge difference of voltage is referred to as a membrane potential. So membrane potential of neurons that is not transmitting a signal is called a resting potential. I hope you should be able to tell the difference between the membrane potential and the resting potential. So the positive, so there's a potential difference between the positive ions or the positive charge outside and the negative charge inside is what we refer to as a membrane potential. But for the membrane that is not conducting an impulse, we say that that neuron is at rest. So the potential difference between the positive charges outside and the negative charges inside, we refer to it as a resting potential. You get the difference? Yes. So you can feel free to drop your questions whenever you want. So now the iron pumps. Now, if you here you need to remember your cell biology. Here it is cell biology that is working. So if you're not okay with cell biology, good enough, I'm recording. After the lesson, you can go back and read some cell biology, especially the protein molecules, and then after you come and watch a recorded video. The topic is going to be good. So within a cell membrane, okay, if I'm to sketch my cell membrane, you have there some protein molecules, okay. Some of them are gated channels, others they are leak channels, they don't have gates, okay. So some they are gated channels, that these channels depending on what they do. Now this one you can call it the potassium, okay, stroke sodium pump. Now this one, what does it do? It pumps both potassium and sodium. But this one can also be just the sodium gated channel. What does it do? It has a gate, and it only allows sodium ions to penetrate through. Okay? Well, you can also have the potassium gated channel. Now these ones, they are specific with potassium, that only potassium ions will be the ones to pass through. Okay? So now these protein molecules within the membrane of a neuron, they are the ones that are responsible for maintaining the resting potential of a neuron. Okay? And how is it maintained? By pumping the sodium ions outside, okay, and then you pump potassium ions inside. Now if you pump sodium ions outside, you have more positive ions, okay, and so more positive charges outside than what is inside, so you have more of the negative charges inside. Is that okay? Yes. So I hope you now know what a membrane potential is. What is even that impulse? Now, before I was introduced to this topic, I don't know even. I used to think an impulse was what? Hmm? But actually, when I was introduced to this topic, I got disappointed. That what I expected an impulse to be was totally different. I got surprised when I saw sodium ions, potassium ions moving, that they are moving, now the impulse is moving. But that is science. That was good confusion, okay? That from that day, then I have to learn what happens. Now, it is a membrane that is not conducting, okay, an impulse that will be able to be stimulated to conduct an impulse. I don't know if you are getting me there. It is a membrane that is not conducting an impulse that can be stimulated to conduct an impulse. So therefore, what does that mean? It means for you to be able to conduct an impulse, then you must be able to form back the resting potential after conducting an impulse. Okay? So now let us see how that resting potential is formed. Now, like we said, now here I'm going to go slowly by slowly. Like we said, we have potassium ions and sodium ions. Okay? That's why you people should eat enough salt. You can even go and check the deficiencies, the deficiency syndrome of sodium ions. So these potassium and sodium ions, they play an essential role in formation of a resting potential and an action potential as well. That their relative concentrations between outside and inside determines whether a neuron is conducting an impulse or a neuron is at rest in preparation for an impulse. Now, a neuron that is at rest, that is a neuron that is not conducting any impulse. The concentration of potassium ions is slightly higher inside. Actually, not just slightly, but it is higher inside. And the concentration of sodium ions is higher outside. Confusing, right? Which is okay. So you can see the neuron that is at rest, it has more concentration of potassium ions inside. Okay? Potassium ions inside. Anyway, those are negatives. Potassium ions inside and more sodium ions outside. And so it is said that the inside is negative and the outside is positive. Now the question is, what is the relationship between potassium ions and sodium ions that make the inside to be negative and the outside to be positive? Okay? In your mind, that should be a question. Okay? If it is not there, then try to answer that question. We are saying that potassium ions, they are high inside, and sodium ions, they are high outside. But the outside is positive and the inside is negative. Are potassium ions negative? Then what makes inside negative? Now, because of these ions, the potassium ions must be maintained inside and sodium ions must be maintained outside. But remember, our plasma membrane is just a phospholipid bilayer, okay, with a long, with these tails having a hydrophilic head and a hydrophobic tails. And these tails, in fact, they make two. Eh? This is a tail and that's another tail, then this is a head. So they make almost such a layer. So in simple terms, these ions being polar in nature, they cannot easily cross, okay, this plasma membrane. In fact, they cannot cross unless guided. So therefore, in your membrane, you're going to have the potassium sodium pumps that are going to pump these potassium ions and sodium ions in and out of a cell. Now, this, it is one pump, it is one protein molecule, but in case the impulse has passed and the inside has been depolarized, let me change some pen, and you have depolarized this, oh sorry for that, you have depolarized this where the inside is positive and the outside is negative, it will mean that you have more sodium ions inside than potassium ions outside. So there is a need to restore the resting potential. So what do? Then these potassium ions, potassium, sodium pumps or sodium potassium pumps, they are the ones that will actively pump these sodium ions from inside a cell and they are pumped outside. Okay? And then the potassium ions which are outside, they will be pumped from outside to inside. So this is inside and then this is out. Now this is where the science is. For every three, I hope that statement is there. Yeah, it's there. For every 3 sodium ions that are transported out, 2 potassium ions, they are transported inwards. Mark that word. Underline that word. Here you transport 3, okay? But here you transport 2. So now it might seem to be like negligible or not that significant. But you see, you have millions, okay, of these protein, of these sodium potassium pumps. But even these millions, each each pumps like 5 times in 1 millisecond. Okay, so what does that mean? It means the positive charges outside, okay, the sodium ions outside, which are the positive charges, they are going to be so high compared to the positive charges inside, that is the potassium ions. So as a result, you have more positives outside and less positives inside. But because you still have the chloride ions inside, you have the proteins inside, and you have the nucleic acids inside, which are negatively charged. Now these ones are negatively charged. Then they will end up making the inside to appear negative and the outside to appear positive. Okay? And it is as simple as that. So it generates a net export of positive charges outside, resulting into a voltage difference. Okay, because of this difference, you have more potassium out, more positive charges outside and less negative charges. Okay, and more negative charges. Okay, so this one creates a voltage potential or a membrane potential. Okay, which is referred to as a resting potential. Is that okay? Yes, I think I've talked about this. Now, also, within this membrane, after you have established this, okay, after you have established this resting potential, you have there the potassium leak channels. Now, these ones, they are not gated. Their pore is ever open. Okay? And so you remember you have transported, you have filled the inside with potassium ions than what is outside. So you have more potassium ions inside than what is outside. So if because of these leak channels are open, then these potassium ions can slowly diffuse, okay, to the outside environment or to the inside environment, depending on the need. Oh my God, depending on the need. Okay, yes. And so if you remove, you remember you had the little positive ions, but still, even the little you had, it is still diffusing through these leak channels. So you end up creating more more negatives inside and less and more positives outside. And so because of that voltage difference, then we call it a resting potential. So allow potassium ions to leak out of a cell, and inside of the cell becomes more negative, more and more and more negative. So as a result, you create what we call a resting potential. So what we are talking basically is here. So you can see this is a neuron, and this is, sorry, so this is a neuron, and then this is a synapse. So they are dendrite. Now we magnified this part and we observed the membrane, the cell membrane. Now if you observe inside, you have there more potassium ions. Okay? Where is my, let me get some different pen so that you can see. So if you observe inside, you have more potassium ions. And if you observe outside, you have there more sodium ions. But the sodium ions, okay, the positive ions outside are so high compared to the positive ions inside. And as if that's not enough, you have the chloride ions inside, which are negatively charged. You have there the proteins, okay, which bear negative charges, and you also have their nucleic acid in the cytoplasm, which also bear negative charges and other negative anions. Okay, So because of that, the inside will end up becoming, yes, negative, and outside will end up becoming positive. So they can't just cross, they cannot cross. These potassium ions, these sodium ions, they can't cross through this. Why? Because they are polar molecules. So if they cannot cross, then they will stay outside, and the chance is when these protein molecules open. If the protein molecules open, then they can easily diffuse in and out. That is if an impulse has arrived. And if you open the gated channels, then there will be an influx of sodium ions inside a neuron or inside the membrane. And then you also open the potassium gated channels. There will be an outflux hmm, of potassium ions. So by doing that, you are destabilizing, you are deteriorating, you are yes, you can use any word, the membrane potential. Okay? And so that deterioration moves along the entire neuron, and is the one which is transmitted as an impulse. So I usually use this analogy to illustrate. Like you assume in your school, how many students are you? You are 1,000. You can imagine. Okay. Now, if I get all the 1,000 students and I put them at the gate and I say, run outside, okay? And the gate is closed. They are going to push themselves, but the gate is closed. No one is going to run out. But the moment I open a small gate, okay, let me open the entire gate because the students are very many. They'll push inside or they will push outside depending on what I want. And then after they have pushed inside or pushed outside, then I tell you, maybe Dennis, maybe Mebra, maybe Jordan, there are two Jordans. I tell you, Jordan, that now I want you to lift these kids one by one, while throwing out. The gate is closed, but you lift these kids one by one while throwing out. Do you use energy? Automatically, yes. Okay? But at first, because the gate was closed and there were 1,000 students at the gate wanting to enter, if you open the gate, there will be an influx of these students inside. So use that analogy here. Okay? So right from the resting potential, from the membrane potential, you have seen that you have more sodium ions outside. Much of sodium ions outside. And more potassium ions inside. Okay? So when you open the sodium gated channels, then there will be an influx. Too much. Okay? But sodium ions inside. And when you also open the potassium ions, there will be too much outflux of potassium ions. So that distortion, that deterioration is what we refer to as an action potential. So let us see. So an action potential, by the way, it follows an or none. What does this mean? We are going to see it in details. That the wave of depolarization must build up to a certain value. Okay? Like you have, this is your membrane potential. This is your membrane, and this one is a resting membrane. Okay? And this will be the resting membrane potential. So it must, if you depolarize this membrane, then you must depolarize up to a certain value. Maybe this is the value. That if you don't reach that value, then this one cannot evoke an action potential, cannot evoke an impulse, cannot evoke an impulse. But once you reach that value, okay, once you reach, then a full potential full. There is no half. There is no half an impulse. Okay? Once you reach this value here, then a full potential is going to be evoked. Okay? And the impulse is transmitted. So that's what it means. Oh, okay? That an action potential is a brief or non depolarization of a neuron's plasma membrane. Okay? So you are depolarizing. And so what happens? Both the voltage gated channels, okay, of sodium and the voltage gated channels of potassium ions, they work equally in depolarization of this membrane, but they don't work at the same time. Actually, should be. By now, you should be asking yourself, why aren't they working at the same time? Okay? Okay, I hope you might answer. Not by now. Oh, sorry for that. So now, they are all involved in the production of an action potential. So you can see these are our gated channels. So here, it is a gate. Okay? And the gate, because of that gate, the potassium ion, these sodium ions, they are restricted outside. Okay? They cannot enter inside. Is it okay? Yes. Oh. So they cannot enter inside. But now, and so that's why you're seeing positive ions outside and negative ions inside. But when an impulse arrives, when you depolarize, now depending, it could be a stimulus. We are going to see how a stimulus is transduced. So if it is a stimulus or it is another impulse reaching this membrane, then you're going to open this gate. Okay? And so if you open this gate, then there will be an influx, a shunt of sodium ions inside this membrane. But remember, the potassium ions are not, they are still inside. So as a result, the inside is going to be more positive than the outside. So the outside we say to be negatively charged. And so this is a membrane in a depolarized state. So when a stimulus depolarizes a membrane, then the sodium channels, let me first mute here. So when an impulse depolarizes a membrane, the sodium channels open, allowing sodium ions to diffuse into a cell, as you can see from here. That is when an impulse arrives. Okay? Now, it is a positive feedback mechanism in that when you open these gated channels, then sodium ions enter into a cell. Now, when sodium ions enter into the cell, the inside becomes more positive, which creates more voltage. Okay? But remember, these are voltage gated channels. So if you make inside more positive, you are creating more voltage, then you'll be opening more of these sodium gated channels. So they will open widely and more. And so if they open widely, then more sodium ions now will diffuse inside. Okay? I hope you can see that. So, more gated channels open to allow more sodium ions inside. Now, when sodium ions reach inside, they will cause a complete depolarization of a neuron and an action potential is created. Now, that action potential created, okay, it will open more of these sodium gated channels more widely so that more sodium ions, okay, increase to enter inside. So in this state, the neuron continues to open more sodium channels to allow the membrane to be depolarized, more depolarized. Okay, and because of that, then you easily build up the membrane, the action potential which is evoked as an impulse. So that positive feedback mechanism can easily explain the all or nothing rule. Now, after you have depolarized a membrane, okay, then you must restore back the membrane potential. Okay, let me illustrate. So you have more positive ions inside. Why? Because there was a shunt, okay, a shunt of positive ions from outside to inside, and you still have more potassium ions inside. By the way, you still have more potassium ions inside. Now, to restore to restore the polarity, okay, to balance the positive charge between what is inside and what is outside, then what do? You open the voltage gated channels of potassium, or you open the voltage potassium gated channels. Okay, and so when they open, what is going to happen? These potassium ions, remember they are specificity. Yes, you have more sodium ions, but these are potassium gated channels. They do allow potassium ions to be the ones to move out. So these potassium ions now, when you open these voltage gated channels for potassium ions, they will now move outside. Okay, so rapid, the movement is going to be rapid. Okay, potassium ions are moving outside. Now, why are they moving out? You have created a positive charge, but to balance that charge, okay, to balance the positive charge, then the positive ions, which are the potassium ions, they will now move out, so that the charge out and the charge inside is kinda balanced. Is that okay? Yes. We are going to see all this. Don't worry. We are going to see. So as the action potential subsidizes, then the inside of a cell becomes flooded with sodium ions. Like how you see. Because you had a shunt. You had an influx of sodium ions inside a cell. So what will happen? You're going to open the potassium gated channels, okay, to allow the potassium ions to move outside of the cell membrane. And so if they move out, you'll be kind of balancing the positive charge. Yes, you have more positives inside because sodium ions, there are very many, like times, should I say times 3? Okay, in the ratio of 2 to 3, you can use that. So you have more potassium ions, sodium ions inside, yes, but you will also open the potassium gated channels so that these potassium ions diffuse out and you balance this positive charge. Okay, and so what happens? The membrane's repolarization is restored. But as if that's not enough, okay, the sodium ions that diffused inside, they cannot stay. Okay, you need to restore back the membrane potential, and we said the membrane potential, you have more sodium ions out and more potassium ions inside, but for you are aiming at balancing the charge. These ions must go back to their original positions. So how is it going to be done? You will have the sodium potassium pumps. Okay, the sodium potassium pumps. Now we are almost going back to where we started from. So you have the sodium potassium pumps within this membrane, and these sodium potassium pumps, what they do is they pump, so they use energy, okay, to pump the other sodium ions that had accumulated here, okay, to pump these sodium ions out. But in the process, the potassium ions, they will also be pumped back inside. But because you have more sodium ions, because sodium ions, they are very many compared to the potassium ions, then as you pump 3 sodium ions, okay, outside, you'll be pumping 2 potassium ions inside. So if you do this, then you restore back the membrane potential. Is that okay? Now, the words have been many. Now, I usually use illustrations. So there is some video game I want us to see. Now you must be wondering that, video game in biology? Yes, for me that's how people learn. You learn by seeing. And we are going to use a so this is a neuron, okay, where I have, these are the membrane, this is a membrane, and if I try to zoom, if I try to magnify, you can see what we've been talking about, okay, where these ones, the keys here, this is a potassium leak channel. These ones, they are ever open, okay, but they are over. Why are they open? Okay, they remain open to allow potassium ions to keep moving so that you restore that membrane potential. Then you have the sodium leak channels. These ones also, they remain kind of open so that sodium ions can continue moving, okay, so that you retain back the resting potential. You have more sodium ions out and more potassium ions inside, okay. Let's first neglect the charge. Then this is the sodium gated channel, this one, and this is the potassium gated channel, okay. That's what we've been talking about, and they are found all over, okay, the cell membrane. So this is our neuron, okay, this is our neuron. Now we are going to stimulate our neuron. And how are we going to do it? If I stimulate, you're going to observe. Now that one is a wave of depolarization. This one, it is our impulse, okay. So the impulse is moving along the neuron, but for us, we have dissected here. We are going to see what is going to happen when an impulse arrives there. So you're going to see, that's pretty good. We can repeat when it is fast. Unfortunately, you cannot stimulate before it restores a membrane potential. So we can show ions and we can show charges also. You can see that the outside is positively charged. Let me zoom so that you can see. The outside is positively charged and the inside is negatively charged. If we stimulate a neuron, we are doing it fast. So I hope you are able to see how the charges change. You can't stimulate it. B. Yes, so that is a video game. Now let's do it slowly as we are observing, as we are studying. So you can also see from this potential chart, you can be able to draw a curve. Now, what is going to happen? Let me first. Now, I want you to observe when an impulse arrives. Let us stimulate together. Observe. Now, this is our impulse. Okay? This is where it is. So the outside is positively charged and the inside is negatively charged. So when an impulse arrives, it is now the impulse has arrived. So are you seeing that now our potassium gated channels, sodium gated channels, they are opening? Are you able to see that? The sodium gated channels are opening. And so the inside is still negative, but the outside is still positive. Maybe. So that is our neuron, and that's what we are trying to stimulate. So now, what happens? Mhm. Are you seeing the potassium ions? Do you see that they are opening widely? The potassium gated channels, they are opening widely. Uh-huh. Are you seeing? But do you see that the potassium gated channels, they first remain closed? Okay. So are you seeing the sodium ions? Uh-huh. I want to see the influx. So are you seeing the influx of sodium ions? Now you have more sodium ions inside. And so therefore the inside is positive and the outside is negative. Somebody saying something? Okay,
The
so
influx of the sodium gated channel and the potassium gated channel, it is antagonistic. They don't open at the same time.
yeah, that's a good observation. And I want you to think about why. Why aren't they opening at the same time? So this one first opens, okay? And there will be an influx of sodium ions. And so the inside becomes positive, okay? But the outside is negative. Why? Now you have not put any negative ions outside. But because of the charge, you have more positive charges inside and less positive charges outside. Then the outside, because of that potential difference, the outside ends up becoming negative and the inside becoming positive. Are you seeing that? Now, after the inside is positive, now therefore, you have to restore, you have to balance the charge. Now in balancing the charge, that's when the potassium gated channels, are you seeing them? That's when they will open. So you can see. Now when they open, potassium ions now will begin to move out. Are you seeing them? Now why are they moving out? You are trying to balance the charge, okay, between what is outside and what is inside. You are trying to balance the positive charge to zero, and by balancing the positive charge from high positives back to zero, and by balancing the positive charge, then you are repolarizing the membrane. But obviously these ions, these potassium ions, they can't stay inside. Sorry, these sodium ions, they can't stay inside, and these potassium ions, they can't stay outside. So what is going to happen? Then you're going to open the gated the potassium pumps, the sodium potassium pumps, and these ones, they will pump the sodium ions out, okay, and the potassium ions inside, okay, and you restore back the membrane potential. So now we can observe the chart, how this chart is going to vary. Uh-huh. And it happens, it is quick, it is quick, it is quick. Hmm? I can use this when it is quick. Are you seeing the chart? Mhm. So that is basically how it is. So this is some nice video game that you can also try at home. You can reduce and see what will happen. You can you can see. So generally, and it happens quickly. Hyperpolarization here, as you are trying to restore back, okay, your resting potential. You have a resting potential, okay. Then there is a wave of depolarization as you are trying to restore, as you are trying to repolarize, okay. Then you overshoot, okay. This is supposed to be the normal, but you overshoot. Now this overshooting, we call it hyperpolarization, and so you give it time, okay. So more potassium ions on the outside, okay, than their sodium ions inside. So remember, you are trying, you pump potassium ions outside, and you try to pump the sodium ions out, so you have more potassium out than the sodium ions that are inside. Okay, so you end up creating an imbalance in the charge. So the inside becomes more negative than the normal negative, the normal voltage that is supposed to be there. So basically that is it, and that's what we have talked about. So even if I don't repeat this, but we shall do. So you can see this is our resting state of a membrane. Okay, and these are the sodium gated channels, and you can see that it is closed. Okay, then this one is the potassium gated channel. Okay, and you can see that it is activated, and this one is inactivated. Okay, so you can pump these potassium ions inside, but you cannot pump them outside. Okay, that's basically how it is. So this is the resting state, and the resting state, you always have more more positives outside and more negatives inside. Okay, so basically that's what it is. So the activation of gates on the sodium or potassium are closed, and the membrane is said to be in a resting potential. Now during depolarization, now here the impulse is going to arrive like how you saw. Then the sodium gated channels open, whereas the potassium remain closed. Okay, so a stimulus opens the activation gates of on some the activation gates. They are these ones. Okay, they are these gates, this gate that is there. So a stimulus open the activation gates on some channels, that is sodium gated channels. And then there is an influx of sodium ions through those channels, which depolarizes a membrane. Okay, and if the depolarization reaches a threshold value, this value here, okay, this value here, this one, then it will be evoked as an impulse. But if it doesn't reach, then it will always go back to the resting potential, always go back to the resting potential, and so on and so on and so on. Okay, now there will be an influx of sodium ions. Okay, and so the inside ends up becoming positive and the outside becomes negative. Okay, so that is the raising phase. Oh, sorry. So that is the raising phase. So you open more, and so more sodium ions enter inside. Okay, and so you gain, you create that curve, this one, up to when you reach the maximum. But it cannot stay there. You have to regain back the membrane potential so that the membrane can now conduct another impulse. Okay, and so it has to fall back. So that is the falling phase. Okay, and so in the falling phase, you open the potassium gated channels, as you can see from here. Okay, you open the potassium gated channels, and so if you open, then there will be an outflux of potassium ions. Is that okay? And pumping of sodium ions out. Here you use energy to pump. So the inactivation gates on most sodium gated channels close, which blocks the influx of sodium ions. Then the activation gates on the most potassium channels open, permitting potassium ions, permitting the potassium ions to efflux. Efflux means moving out, which again makes the inside of the cell more negative. So as simple as that. So it is all about balancing a positive charge. You enter, sodium ions enter inside, Okay, and then if sodium ions enter inside, then the inside becomes more positive, and so that one we call it the action potential. Okay, the membrane is said to be depolarized. But to balance the positive charges, then the outside, the potassium ions, the potassium gated channels open, and there'll be an outflux of potassium ions, so that now you balance the positive charge, and so the inside now becomes negative again. But there is undershooting. Now undershooting, we call it hyperpolarization, and in this one both gets the sodium channels across it, but the activation gates on some potassium channels are still open. So as a result, most of the potassium channels as these gates close most of the potassium channels, and the inactivation gets open on sodium channels, which and the membrane returns to its resting state. Now here we are trying to regain, but anyway, with hyperpolarization there is undershooting of potassium ions, so that you have more potassium ions than what is required. So basically that's as simple as that. So in case you have a question, then this is the right time to ask for the question. We have seen how an action potential is formed, is produced by opening the gated channels, then efflux, blah blah. So how is it going to be conducted? Okay, right from where it has been produced up to when it reaches the final destination. If it is brain, if it is the effectors, if it is the muscle, then how is it going to reach there? It is just simple. The impulse just moves as a wave of depolarization. What we have just explained in the above slides, it is what moves. Okay? From here it happens, then it jumps from here, then it continues from here, continues from here, from here, up to when it reaches the brain cells. Okay, but it occurs, it is rapid, it is rapid. Okay, that in just milliseconds you'll be able to conduct an impulse to the target organ, and you respond accordingly. Just think about how you withdraw from a hot object. Okay, it is rapid. So but it is just a wave of depolarization. What we have just explained in the above slides, it is what happens here. So the action potential can travel long distances. It can travel long distances by regenerating itself along an axon. Like it's we have already. So if you depolarize, here we magnified this part. Okay. So if this part gets depolarized, okay, then it depolarizes this part also, as this part is repolarizing. Okay, then this depolarizes this part as this part is repolarizing, repolarizes this part, sorry, depolarizes this part as this part is repolarized, and so on. So this wave, okay, it continues throughout. Okay, right from the reception, from the point of reception throughout the neuron, okay, up to when it reaches the brain, and the brain also interprets the message and sends the same wave of depolarization that will travel through the motor neurons to the effector organs to receive a response. So basically, it is as simple as that. So at the site where the action potential is generated, that is in the receptor organs, maybe the eyes, maybe the tongue, maybe the skin, or even the sensory cells, where you're going to generate an action potential. And there are two ways how an action potential is generated. One, it could be by depolarization, like how we have seen, where you form more positive ions. Like the depolarization opens the sodium gated channels so that you have an influx of sodium ions inside. Or hyperpolarization, you hyperpolarize, okay? That instead of opening for sodium gated channels, you open for chloride ions, okay? And if you open for chloride ions, you can imagine they will just diffuse inside, okay? And they will end up making inside more negative than outside. And so we call that one hyperpolarization. So there are some cells that are stimulated by depolarization, and there are other cells that are stimulated by hyperpolarization. But when a cell is stimulated, or when an organ is stimulated, then the whole of this happens and an action potential is evoked. Now that action potential, it is the one that will travel through this as a wave of depolarization. Okay? So therefore after that, then an electrical current depolarizes the neighboring region of the axon, and so on, and so on, and so on, until when you reach your target organ. So it is as simple as that. Okay? So there is nothing hard. Let me first wrap this part. So number one, an action potential is generated as sodium. Let me change a pen. So an action potential here, we had what happens here, but we have already seen. So an action potential is generated as sodium ions flow inwards across the membrane at one location. Okay? And so here, this part is going to be depolarized. And so if that part is depolarized, then what happens? Then the wave of depolarization, or the depolarization of the action potential, spreads to the neighboring region on the membrane. Okay? Reinitiating the action potential there, I mean here, in this neighboring region here. Okay? Now, the question is, why isn't it moving this side? Like, you depolarize here. Why isn't it go backwards? Why doesn't it move backwards? Why? 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 Yes. Think about it, and I'll give you the answer. The answer is refractory period. Okay? Now, this is a period when a neuron that has conducted a nerve impulse cannot be stimulated again. You saw it from my simulation. After clicking and the action potential happens, I couldn't be able to stimulate it again. I will show you before ending the lesson. We call that one a refractory period. Now, here, this part has already, let me change a pen. This part has already conducted an impulse. Okay? And now this part is undergoing depolarization. Now, why isn't it going back? It's because this part here, which is under refractory period, cannot be repolarized again. Okay? Whereas this one now can be repolarized. This part can be repolarized, but this part cannot be repolarized. This part here cannot be repolarized. So as a result, there is, yes, you have sodium ions, yes, it is just a wave which doesn't have direction, but it cannot spread backwards because this part is under refractory period. So it will always continue in one direction. Is that okay? Does it make sense? Then the third region is the depolarization. It is there. To the left of the region, the membrane is repolarizing as potassium ions are flowing outwards. Okay? So you cannot depolarize it again. The depolarization and repolarization process is repeated in the next region of the membrane. Okay, and in this way, local currents called graded potentials of ion across the plasma membrane cause the action potential to be propagated along the axons. And you'll be able, by that, you'll be able to transport your nerve impulse from the point of perception, okay, up to where it is, up to the target of the neuron, okay. But after stimulating, I can't stimulate it again. Even after the impulse has been evoked, I can't stimulate it again. Now, not until now that period, this period, it is called refractory period. Maybe let me take it slow. Let me take it normal, because slow you'll be too slow for life. Maybe let me show you a chart. This is where the depolarization is. This one. And that is where that's where an action potential is evoked. But this one is just to regain. Okay? It is just for regaining. So now you see. Let me clear. Now if I do this, now that is where the action potential is. Now from here, it will be to the next level. Once it reaches here, it proceeds to the next level. Now the whole of this, it is the regaining process to prepare a neuron to receive another impulse. Now the whole of this process, this regaining process, it is called a refractory period. You cannot stimulate. I'm trying to click. I hope you are hearing the clicks. It can't be stimulated. Even it cannot be stimulated. Not until it restores back the membrane potential. Then it will be able to be stimulated. Now I can stimulate it again. Now that will be another impulse. Okay? But I cannot stimulate it. So the whole of this, it is a refractory period. I can't stimulate it again. I can't still. Now I can. So basically that's how it is. So now a refractory period, it is that period where a neuron cannot be stimulated. Why? It is the period of putting everything back to normal. Okay? Everything back to normal. So after you've depolarized the membrane, okay, it cannot stay in that depolarization state. Otherwise, it cannot receive enough impulse. It can't. So what happens is you have to repolarize the membrane so that you restore the resting potential to be able to receive enough impulse. So that period is called a refractory period. So while the neuron is busy returning everything to normal, I've already talked about this. It cannot respond to any incoming stimulus. So in this period, even if you do like wow, you cannot. Okay? You cannot. So even when you are studying reproduction, you'll be able to see that males have this refractory period. You'll be able to find it. Let me not talk about reproduction now. So after the sodium stroke potassium pumps return the ions to their rightful side of the neuron, then the neuron is back to its normal polarized state and stays in a resting potential until another impulse comes in and depolarizes the membrane again. So basically it is as simple as that. I'm going to stop here. I'm going to stop here. What's the time?